Discriminant analysis. So still under classification techniques, right? So chapter number 4, we have learned logistic regression and naive Bayes. So for discriminant analysis, it's actually multivariate techniques. It's a multivariate techniques concerned with separating distinct set of object and allocate new object to previously defined group. Basically, we want to separate two object by decision boundary. So we need to create a decision boundary to separate two groups. Right? Either group y equal to 0 and y equal to 1. Right. So the goal is to describe either graphically or algebraically the different features or observation from several discriminant from several observation. Right. Discriminant is versatile. This one you can read by yourself lah. Right. So as I said just now, we want to create a decision boundary from two groups to differentiate two groups. So we want to draw a line, linear line to differentiate two groups. So this line called as decision boundary. Right. So remember in logistic regression, we make our decision boundary macam mana? When the probability more than 0.5, we classify y equal to 1. When the probability less than 0.5, we classify y equal to 0. That is our decision rule for classifying data. Right. In this case, we define the classification the decision boundary by probability of y equal to 0.5. Sorry, y equal to y given x equal to this is y equal to 1 given x equal to probability of y given 0 given x. So it means that when the value are equal, this is our decision boundary, right? So it's also known as a supervised machine learning to solve multi-class classification, same as naive Bayes and logistic regression. Right. It's also known as normal discriminant analysis or discriminant function analysis. Right. As I said just now, for naive Bayes is a generative framework, generative model. Generative model means it follows a stochastic model. It imposes a random operation. So linear discriminant analysis also follows generative framework. It's impose random generation, right? So the reason why we learned naive Bayes previously, because in linear discriminant analysis also use Bayes theorem to classify new data point. So basically, in fact, we already learned in how to calculate the probability of continuous data in naive Bayes, right? So the class that get highest probability is the output class, and make the prediction is made. So basically, we want to create this decision boundary based on the class posterior probability. Give the highest value will be classified as that class. Right? Let's say we need to calculate discriminant score for class 0, discriminant score for class 1. So which one is the highest? So same as naive Bayes concept. Right? If the class for 0 is higher, so then the value will be classified as 0. Okay. So in linear discriminant analysis, I already explained this now. We want to draw a straight line that completely separate two class of data point, right? So the assumption, this is the important part, right? We know in naive Bayes, the assumption is the class conditional are independent and And what? In naive Bayes. Tadi baru ajar. What is the assumption of naive Bayes? Independent. Yes, the class conditional is independent, right? And then we're going to use Bayes theorem to classify the data. Now, in linear discriminant analysis, the input data set should be assumed as Gaussian distribution, which is a normal distribution. So since we assume a normal distribution for a independent variable, it means that it can only take the quantitative variable as independent variable. Boleh faham? So in naive Bayes, it can take categorical variable and quantitative variable as independent variable. But for a linear discriminant analysis, can only take quantitative variable as independent variable. That's why we assume the data input data set should be normal distribution. Right? So then we can draw a linear line, meaning that we can draw a straight line or decision boundary that separate data point. And another assumption for linear discriminant analysis, each class has a same covariance matrix. It means that the variance for class y equal to 0 also equal to variance y equal to 1. This is a really happen if you have many class and you have high dimensional data. So that's why in linear discriminant analysis might not well perform in high dimensional data. Right? High dimensional data means what? You have very large independent variable, right? Such as a genetic variable or image data set. Right? So this is two major assumption. First, we assume the independent variable came from a normal distribution, and each class should have an equal variance, right? So, as I said, the linear discriminant analysis is based on Bayes theorem. So we already learned Bayes theorem just now. So this is what we call as posterior probability. This is a class conditional, and this is a prior probability, and this is our marginal probability. And our goal is we want to predict y equal to what, y given x. This is our goal, y given x. Same as naive Bayes. The only difference is the independent variable assumed to be normally distributed, and each class should have equal variance. Right. So if the class have no equal variance, we cannot proceed with linear discriminant analysis. We should go for quadratic discriminant analysis. So this is the class boundary that I mentioned just now. We want to create a linear line, right? Decision boundary where the probability of y given x, y equal to 1 given x equal to y equal to 0 given x. Right? We want to separate these two observation, these two class. So the problem with Bayes classifier, it depends on the quantities that are known, right? So that's why the class conditional, right, is unknown, right, in Bayes. So that's why we assume the class conditional to be a Gaussian distribution. And that is the thing that I already mentioned. So in classification, there are three approaches in classification method, right? First is empirical risk minimization. It means that we compare all classifier available that's suitable for the data, and we measure the performance of each classifier. Choose the classifier that give minimum true error rate by comparison. Let's say we have a data. This data have a binary dependent variable, We can model it by using logistic regression. We can model it by using like naive Bayes, and we also can model it by linear discriminant and many more. We have random forest, support vector machine, and so on. Right, and we compare all the performance. We take the classifier that give the minimum error rate to be the best classifier to do a prediction. That is a first method by empirical risk minimization. The second method by using regression. Right? By regression, we can estimate the probability of X, right? And by using the decision rule, we just learned this one last week. When the probability is more than 0.5, we classify as 1, less than 0.5, classify as 0. So the third classification approach for classification and the probability, the class that give highest probability, we classify to that class. Now, so this linear discriminant analysis will use the third approach, right, where we want to compare the probability value. But in this case, we're not going to straight away compare the probability value. We're going to compare by using discriminant score, which is a delta value, right? So this is a repeated thing, right? Based on Bayes theorem. Now we're going to use, instead of probability of X given Y, right? This is a class conditional. So we're going to use another function symbol, which is F1X. This is pi 1 means that the prior probability, right? This is not 3.14. This is pi means the probability of class K. And this is a marginal probability. So since we assume the class conditional to be a Gaussian distribution, so we're going to use a normal distribution, Gaussian function, right? It's the same as previous, right? Boleh faham? Right. So and another function assumption is assume the variance for each class are equal. Right? That's why we need to measure the equality of variance before we start performing linear discriminant analysis. Right. So now let's look at linear discriminant analysis when we have only one predictor. That means one independent variable. And remember, the independent variable or predictor should be continuous. Right? You cannot use linear discriminant if the independent variable is categorical. So we assume the Gaussian distribution, right? And then we need to calculate the mean and variance for each class, right? So, but the variance we should not calculate for each class because we already assume the variance for each class are equal. So we need to calculate pool variance or pool standard deviation. We need to pool all the variance together, right? Right. So this is the formula, right? So I have a note to prove this one, but I'm not going to prove in this class. Maybe later I will post a video how to prove from a Bayes theorem to this formula, right? So basically, delta K came from a Bayes theorem. The formula that we look at this one, right? F for each class and divide by n minus k. K is the number of class, n is number of observation. So now let's look at example number 1. I think this example I already provide the answer. Right. Okay. Now, example number 1. So how many observations we have here? No, we have 5. So this one not yet classified. We want to predict when balance equal to 900, what is the default value? Right. So for first step, we need to calculate the mean for each class. So this is a class for default equal to 0. We need to calculate the mean. So this one should be 500 plus 245 plus 1970 divided by 3. So we have 3 observations. So we will get 931.67. This is the concept. Later on, we will look at how to calculate in example number 2. Right. So for the second mean, when this is where default equal to 0, this is default equal to 1. So we have 2 observations only. So 7390 plus 2845 divided by 2. So we will get 5117.5. Now, the prior probability for y equal to 0, right? Maybe we put like this, d equal to 0 is 3 over 5. Right? Probability of d equal to 1 is 2 over 5. This is the prior probability. Now, once you already obtain the value of mean for each class and the prior probability, right? So we need to calculate the pool variance. So pool variance is summation of xi minus mu k square divided by n minus k. So in this case, we take this one 580 minus the mean for d equal to 0 is 931.67 square plus this is 245 minus 931.67 square plus 1970 minus 931.67 square plus 7390 minus the mean for class number 2 is 5117.50 square plus 2845 minus 5117.5 square. Divide by n minus 1, n we have 5 minus k, n minus k. K we have 2 class, k equal to 2. So 5 minus 2. So that's why we got 3. So this is 4000. How much? 400,609.72. You need to calculate that and then you will get the exact value. This is the exact value, right? Okay, so next, once you already have the value of mean, variance, and the prior probability, so we input into the delta function. So delta 0 when d equal to 0, and we want to know x equal to 900, we'll classify as 0 or 1. So input the value into the formula. This is 900 multiplied with mean of delta 0, d0 is 931.67 divided by, what is the variance? 400,609.72, right? Minus 931.67 square divided by 2 multiplied with 400,609.72 plus with the log base 10 of our prior, which is 3 over 5. So you will get negative 0.1207395. So please do the calculation and confirm the value. Right, this is the first one. The second part is when class equal to 1, right? So the same step, 900 multiply with the mean of second class, 5117.50, right? Divide by 400060972. Right? This is simple because we assume the variance equal. So this one should be 5117.5 square divided by 2, 400,609.72 plus log the prior. What is the prior? 2 over 5. This is a log base 10. Should be equal to negative 2.52. And then we do a comparison. So since delta 0, 900 is larger than delta 1, 900. So the x equal to 900 will be classified as 0. Okay. So then x equal to 900 will be classified as b equal to 0. Right. Boleh? Any questions so far? It's the same concept since you already understand the Bayes theorem, but in this case, not really. We not straight away use Bayes theorem. We just use the function that derived from a Bayes theorem. So this is the function that derived from Bayes theorem. Okay. Any questions so far? So if you don't have any question, let's look at example number 2. So in example number 2, it's the same concept. We have one observation, one predictor. So let's highlight this one so we can easily calculate the value. So we want to perform a linear discriminant analysis for one predictor and predict 152 lies for male or female. Right. So first step, mu male should be equal to 169 plus 142 plus 168 plus 160 plus 172. Divide by how much? How many observation? 5, right? So this one should be equal to, can you calculate? So give me the answer. This is 140 plus 145 plus, maybe 135 plus 165, 41, 159, divide by, how many observation? 6, right? So what is the value of mean male and mean for female? Mean height for male, mean height for female. Value? Berapa? You should have calculator, okay? What calculator you have? You punya calculator apa? Sorry? 162.2 for male, for female? 7.5. Right. Okay, so we have the value of mean. Now we need to calculate the variance. So variance is summation, double summation of xi minus mu k divided by, and this is square, divided by n minus k. So the first part, let's calculate for male, 169 minus 162.2 square plus 142 minus 162.2 square plus, we need to calculate every semua lah. So all divide by 11 minus 2. So can you calculate the answer? So what is the answer? One point 14261. Are you sure? Semua dapat sama? You got 142 eh? You should get 143, right? Berapa you dapat? 142 juga. Dapat 142. Right, so 140 lah, we use this formula lah, value lah. So now, we need to calculate the probability of Y equal to female and probability of Y equal to male. So this one should be, female is 6 over 11 and this is 5 over 11. Now, so we want to predict X equal to 152 should be male or female. Right, so this is delta M, so 152. So this one 152 multiply with the mean of male 162.2 divided by the standard, the variance is 142.61. So this is based on your value, okay? So this is 162.2 square divided by 2 multiply 142.61 plus log 5 over 11. Right. The next one is female, 152. So 152, this is female how much? 147.5 divided by 142.61 minus 147.5 square divided by 2 multiply 142.61 plus log 6/11. So what is the answer for delta M? Delta M, how much? $80.3. The for female? 80.67. So based on this value, the delta F 152 is larger than delta M 152. So we can classify a person with X height equal to 152 to be female. For example, maybe this is just theoretical lah. Tak betul ke tak? Right. Okay. So example number 3, when we have more variables, right? Say in this example, I already provide you a Python code. You can go to my website. Lambat dia buka. So here I have example number 3, Python codes. So you can see how I proceed with the linear discriminant analysis, right? From exploring data, right? Data exploration, and then what I did is before we start with a linear discriminant analysis, we need to check the assumption. The first assumption is the data should be numerical, right? So if you look at this one, all the data are numerical. Like this one, right? Where is it? So all the data are numerical except cardio, right? And second assumption, we need to check for equality of variance. So for equality of variance, I'm using box M method to check equality of variance. So based on the box M, you can see that the statistic is 17,000. The p-value is less than 0.05, right? It's not zero lah. Basically, it's less than 0.05. Very small. The hypothesis for equality of variance, null hypothesis, hypothesis, the data has equal variance. Alternative hypothesis, data has no equal variance. The equality of variance is not assumed. Right. So since the p-value less than 0.05, we reject null hypothesis. We accept alternative hypothesis. So the conclusion will be the the equality of variance not assumed. Right. For this data set, the equality variance not assumed. We cannot proceed with the linear discriminant analysis by right. Right. So we need to proceed with quadratic discriminant analysis. But for the sake of knowledge, I just perform linear discriminant analysis juga. Right. So when I perform, I'm going to check the model accuracy. So we have accuracy equal to 59.87, right, for this data set. So this is because the equality of variance not assumed. If the equality of variance is assumed, maybe the equality will be higher than this, right? So, and then I do a prediction when height equal to 160, 68 and so on. What is the classification of the person? Ada cardiovascular heart disease or no cardiovascular heart disease? Right, so I'm using two methods. First by using formula, another one by using a standardized method, right? So you can check how to perform these codes in my website. Right, so QDA versus LDA. QDA means quadratic discriminant analysis. The only difference is the equality of variance. Right. The first variable quadratic discriminant analysis, the equality of variance not assumed. Right. So that is the only difference. You can see in my slide here. QDA assume each class has its own covariance metric, different with linear discriminant analysis. That is the only difference. Okay. Then this is the application of linear discriminant analysis. You can read by yourself, right? And the summary for chapter number 4. So logistic regression based on logistic function, right? Logic function P. The logic is log P divided by 1 minus P, and we want to find the maximum likelihood. Naive Bayes, the independence of the variables. The linear discriminant analysis, normal distribution, same covariant metric. Quadratic discriminant analysis, normal distribution, different covariant metrics. Right? So since we finished chapter number 4,